Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us into the vastness of space, to the mysterious and unbounded world of alien life. Look up at the velvet blanket of the night sky, dotted with innumerable points of ancient light, and you are participating in a ritual as old as consciousness itself. For as long as humanity has stood upright on this quiet sphere, we have cast our gaze upward, wondering if other eyes, perhaps vastly different from our own, are looking back across the cosmic ocean. It is a question that does not demand a frantic answer, but rather invites a slow, contemplative wonder that settles deep in the soul. The sheer scale of the universe, with its billions of quiet galaxies, each a harbour for billions of stars, suggests that life might not be a lonely miracle confined to our pale blue dot, but a common song sung in many different keys throughout the cosmos, waiting patiently for us to hear it. Tonight, we do not seek startling revelations or fearful encounters, but rather the peaceful hum of possibility. We drift through the gentle scientific theories and the patient, decades-long search that defines our reach for the stars. We will explore worlds where vast oceans sleep beneath miles of protective ice, and distant suns that warm planets we can only imagine in our deepest dreams. It is a journey of immense distances and tranquil silences, where the very act of searching is a form of connection with the great unknown that surrounds us, holding us in its vast, strangely comforting embrace as we drift along the currents of space-time. If you enjoy these quiet explorations, I invite you to like, subscribe, or share a thought below. It helps other curious minds find a place to rest. But for now, get comfortable. Let your eyes grow heavy. Let's begin. The Drake equation attempts to quantify the number of active, communicative civilizations in our galaxy. In 1961, astronomer Frank Drake stood before a quiet gathering of colleagues in Green Bank, West Virginia, hoping to bring order to a conversation that had previously been pure speculation. The cosmos felt impossibly vast, a shoreless ocean of stars, and humanity needed a way to chart the potential islands of intelligence within it. It was not meant to provide a definitive number, but rather to frame the immense questions that needed asking. The equation itself is a graceful string of 7 variables, each representing a specific cosmic hurdle that life must clear to reach us. It begins with the rate of star formation, then narrows its focus to those stars with planets, and further still to planets capable of supporting life. It delicately asks how often life actually arises, how often it gains intelligence, and how often it learns to send signals across the void. The final term, perhaps the most poignant, is L, the length of time such a civilization releases these signals before falling silent. It transforms the chaotic unknown into an organized sequence of probabilities, a roadmap for future explorers to follow patiently. Even without a final answer, the equation serves as a comforting reminder that we are asking the right questions. It stands as a mathematical expression of human hope, a structured way of looking into the dark and believing there is something more than just silence waiting for us. Astronomers search for planets in the habitable zone, where conditions might be just right for liquid water. Every star, from the dimmest red dwarf to the most brilliant blue giant, casts a sphere of influence around itself, a region of warmth in the cold expanse of space. Within this sphere lies a very special, narrow band that astronomers have affectionately named the Goldilocks zone. It is a concept born from our own delicate existence, a realization of just how fortunate Earth's placement truly is. In this temperate ribbon of space, a planet receives neither too much untamed heat which would boil oceans into vapor, nor too little, which would lock them endlessly in ice. It is a delicate thermal equilibrium where water, the magical solvent that allows the complex chemistry of life to dance and mingle, can exist in its liquid form on the surface. This zone is not fixed. It drifts slowly outward as a star ages and brightens over billions of years. A moving harbour of safety that planets might enter or leave as eons pass. Finding a world in this zone does not guarantee life, but it offers the most promising cradle we currently know of. It is a reminder of the fragile balance required for complexity to flourish. In the vast, often harsh theatre of the universe, these rare oases of temperate calm are like quiet gardens waiting to be discovered. Life on Earth thrives in extreme environments, suggesting alien life might be more resilient than we once thought. For centuries, we believed that life was a delicate flower, capable of existing only in mild, sunlit environments similar to our own comfortable meadows and forests. We projected our own fragility onto the cosmos, assuming that any world slightly too hot, too cold, or too acidic would be forever barren. But our own planet has slowly taught us a different, more robust lesson about tenacity. We have found vibrant communities of microscopic organisms known as extremophiles, flourishing in places that should be lethal. They sleep comfortably in the crushing black pressures of the deepest ocean trenches, thrive happily in the boiling, sulphurous waters of volcanic springs, and endure patiently inside the frozen ancient ice of Antarctica. Some even feast on radiation that would be instantly fatal to us, turning poison into energy. These tiny titans prove that life is not merely a fragile accident, but a stubborn, adaptable force that finds a way to cling to existence against staggering odds. Their existence dramatically widens the canvas of possibility for biology beyond Earth. If life can prosper in the darkest corners of our own world, countless harsh planets across the galaxy suddenly become candidates for hosting their own quiet, enduring inhabitants. Water is considered essential for life as we know it, due to its unique chemical properties. In the grand biochemical recipe of existence, water is far more than just a passive backdrop. It is the master facilitator of nearly every vital process. Astronomers and biologists alike follow the mantra, "Follow the water," because this simple molecule, composed of one oxygen and two hydrogen atoms, possesses almost magical capabilities. It is often called the universal solvent because it can dissolve more substances than any other liquid, creating a rich primordial soup where complex molecules can meet, interact, and begin the long dance of evolution. Furthermore, water has the incredibly rare ability to remain liquid over a wide range of temperatures, providing a stable, long-term environment for delicate life to develop, without being constantly frozen or boiled away. Perhaps most wondrously, when it does freeze, it becomes less dense and floats, forming an insulating layer of ice on top of lakes and oceans that protects the liquid depths below from freezing solid during long planetary winters. This unique characteristic may have saved early life on Earth during its coldest epochs. Water is the gentle cradle of chemistry, a protective and enabling substance that seems almost perfectly designed to nurture the spark of biology in a chaotic universe. Carbon is the likely backbone of alien biology because of its unparalleled ability to form complex chains. When we imagine the architecture of alien life, we almost always return to carbon as the fundamental building block. This is not merely Earth-centric bias, but a recognition of carbon's extraordinary chemical versatility that no other element on the periodic table can quite match. A carbon atom is like a master connector, possessing 4 valence electrons that allow it to form stable yet flexible bonds with a vast array of other elements, including itself. This unique property enables it to build the incredibly long, intricate chains and complex 3-dimensional ring structures necessary for life, such as DNA, proteins, and vast energy storage molecules. While science fiction often speculates about silicon-based life, silicon bonds are generally too strong and rigid to allow for the dynamic breaking and reforming that metabolism requires, or too weak to hold together complex genetic information. Carbon strikes the perfect, elegant balance between stability and reactivity. It is the great cosmic Lego brick, abundant throughout the universe, patiently waiting in interstellar clouds and on young planets to be assembled into the infinitely varied structures of living things. Radio waves are considered the most likely medium for interstellar communication. If a distant civilization wanted to reach out across the staggering distances of the Milky Way, they would likely choose a method that is fast, efficient, and capable of cutting through the cosmic dust. Radio waves, a form of light invisible to our eyes, travel at the maximum speed possible, the speed of light, and can pass relatively unhindered through the vast clouds of gas that obscure much of our galaxy. Furthermore, generating radio signals requires relatively little energy compared to trying to shine incredibly bright lasers across light years. There is a specific quiet window in the radio spectrum, famously known as the water hole, which sits between the natural frequencies of hydrogen and hydroxyl, the 2 components of water. It is a naturally silent channel in the cosmic background noise, a perfect, serene place for diverse civilizations to agree to meet and listen, like travelers finding a quiet clearing in a noisy forest. We listen there because it is logical, efficient, and poetic, a universal meeting ground where different species might instinctively know to look for one another. The Voyager Golden Records are currently carrying messages from Earth into interstellar space. Launched in 1977, the twin Voyager spacecraft were destined to explore the outer giants of our solar system before drifting endlessly into the void beyond. Bolted to the side of each probe is a gold-plated phonograph record, a 12-inch time capsule intended as a hopeful greeting to any intelligence that might one day find it. These records contain a carefully curated symphony of Earth, the sounds of wind, thunder, and surf, the songs of whales and birds, greetings spoken in 55 ancient and modern languages, and an eclectic mix of music ranging from Mozart and Bach to Chuck Berry and Blind Willie Johnson. They also carry encoded images of human anatomy, our diverse cultures, and our location in the galaxy relative to nearby pulsars. It is a message in a bottle cast into the grandest ocean imaginable, likely to outlast humanity itself by billions of years. As they drift silently through the dark, they serve as a touching monument to our existence, a declaration that we were here and that we yearn to share our song with the universe. The sheer number of exoplanets discovered suggests habitable worlds may be common. For most of human history, the other stars in the sky were just points of light, and we could only wonder if they were accompanied by their own retinues of worlds. It was only in the very recent sliver of our history, primarily through missions like the Kepler Space Telescope, that we received a definitive answer We now know that planets are not rare cosmic accidents, but standard features of star formation, vastly outnumbering the stars themselves. In our Milky Way galaxy alone, estimates suggest there are hundreds of billions of planets, many of them rocky worlds similar in size to Earth, orbiting peacefully in the habitable zones of their parent suns. The sheer statistical weight of these numbers has fundamentally shifted our perspective from questioning if there are other places for life to flourish, to wondering where the nearest ones might be. It paints a picture of a galaxy teeming with potential stages, an endless archipelago of worlds where the drama of life might be playing out in forms we have yet to imagine. The theory of panspermia suggests life might travel between worlds on comets or meteorites. Life may not need to begin completely from scratch on every world where it is found. It might instead be a cosmic traveler, hitchhiking across the void. The hypothesis of panspermia proposes that hardy microbial life, or at least the complex organic building blocks required for it, could be blasted off one planet by a meteor impact and carried through space to seed another. We know that certain microscopic organisms on Earth can survive the intense vacuum and radiation of space for extended periods, perhaps long enough to survive a journey to a neighboring planet, if encased deep within a protective rock. It is even possible that life on Earth began on Mars billions of years ago, when it was warmer and wetter, before arriving here on a wayward meteorite. This idea beautifully connects the cosmos, suggesting that biology might be a shared heritage among neighboring worlds. A grand chain of life linking planets together across the cold distances that separate them. Theoretical silicon-based life would likely require very different planetary conditions than Earth. While carbon is the reigning king of biochemistry on Earth, science has long been fascinated by its nearest chemical cousin on the periodic table, silicon. Like carbon, silicon can form 4 bonds at once, theoretically allowing it to build complex molecules. But it is heavier, its bonds are generally more rigid, and it struggles to form the long, stable chains that carbon manages so effortlessly in mild temperatures. For silicon-based life to exist, it would likely need an environment that seems utterly hellish to us, perhaps a world with extremely high temperatures where silicon compounds become more fluid and reactive. Instead of exhaling carbon dioxide as we do, such creatures might exhale solid silicon dioxide, essentially sand, which would pose a significant biological challenge to overcome. If such life exists, it would likely be slow-moving, crystalline, and rock-like, thriving on worlds where rivers of molten lava flow instead of water. It is a reminder that our definition of life might be far too narrow, and that biology could wear many strange masks in the diverse environments of the universe. The Fermi Paradox asks why, in such a vast universe, we have not yet detected any signs of alien civilizations. It is a simple question that carries profound weight. If the universe is so old and so full of stars, where is everybody? Italian physicist Enrico Fermi famously posed this during a casual lunchtime conversation in 1950, and it has haunted our search ever since. Given billions of years, even a slow-moving civilization should have had ample time to spread across the galaxy, or at least send out signals that we couldn't miss. The fact that we are met only with what appears to be a great silence is a deep mystery that has spawned countless theories. Perhaps civilizations are incredibly rare, or perhaps they tend to stay quiet, preferring introspective virtual realities to interstellar expansion. Or maybe, more comfortingly, we are just the first to arrive on the galactic stage, the elder siblings who will one day welcome others. Rather than a frightening void, the silence might be a blank canvas, a vast, quiet space waiting for us to fill it with our own future. Ancient Greek philosophers were among the first to speculate about the plurality of worlds. The idea of alien life is not solely a modern product of telescopes and spaceflight. It is an intuition as old as philosophy itself. More than 2,000 years ago, Greek atomist philosophers like Metrodorus of Chios looked at the natural world and drew grand conclusions about the cosmos. He famously argued that it would be as unnatural for a single ear of wheat to grow in a vast, fertile field as it would be for only one inhabited world to exist in infinite space. They believed that the same constituent seeds of reality, atoms, that formed Earth, were present everywhere, inevitably coming together to form other Earths, other suns, and other living beings. These ancient thinkers did not need data to feel the truth of cosmic abundance. They felt it through pure reason and analogy. It is a humbling realization that our modern search with radio telescopes is the technological continuation of a very old human dream, a persistent whisper in our collective mind that we have never been truly alone. Spectroscopy allows astronomers to search for biosignatures in the atmospheres of distant exoplanets. We do not need to physically travel to distant worlds to learn their deepest secrets. We can touch them with our telescopes by analyzing the light that has traveled across the ages to reach us. When a planet passes in front of its host star, some of the starlight filters through its atmosphere, and the various gases present there leave unique chemical fingerprints in that light. By spreading this light out into a rainbow spectrum, astronomers can read these fingerprints to see what the air of another world is made of. They are hunting for biosignatures, gases like oxygen, methane, and ozone, coexisting in combinations that would be chemically impossible without life constantly replenishing them. It is a delicate, difficult art, like trying to see a firefly next to a massive searchlight from thousands of miles away. Yet this technique is our most powerful tool for finding life right now, allowing us to sniff the air of alien worlds from the comfort of our own pale blue dot. Cosmic timescales mean civilizations could easily miss each other by millions of years. The universe is roughly 13.8 billion years old, a span of time so vast it defies true human comprehension. In contrast, our own technological civilization, capable of sending radio signals, has existed for barely a century, a fleeting blink in the deep time of the cosmos. It is entirely possible that countless civilizations have risen, flourished, and gently faded away long before Earth even cooled from its molten state, or that others will only just begin to tend their first fires long after our sun has exhausted its fuel. We might be like ships passing in an incredibly large and dark ocean, separated not just by unimaginable distances of space, but by unbridgeable chasms of time. This realization adds a poignant layer to our search. We are looking not just for contemporaries, but perhaps for the faint, enduring echoes of those who came before us. It teaches us patience, reminding us that the galaxy operates on a majestic clock far slower and grander than our own. Project Ozma was the first modern scientific attempt to detect interstellar radio signals. In the quiet spring of 1960, a young astronomer named Frank Drake turned the massive 85-foot radio telescope at Green Bank toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He named the experiment Project Ozma, after the princess in L. Frank Baum's distant, imaginary land of Oz. For roughly 150 hours over nearly 4 months, he tuned the great ear of the telescope to the 21-centimeter frequency, listening for any artificial patterns that might rise above the static hiss of the natural cosmos. Although he heard nothing but the random noise of the universe, and one false alarm that turned out to be a secret military aircraft, it was a watershed moment for humanity. For the first time, we had stopped merely wondering if anyone was out there, and had actively begun to listen. It transformed the search for alien life from science fiction into an empirical, respectable scientific endeavor that continues to this day. The Arecibo message was a powerful radio signal deliberately sent toward a distant star cluster in 1974. To celebrate a major upgrade to the Arecibo Observatory in Puerto Rico, humanity decided to shout a ceremonial greeting into the void. The message, devised largely by Frank Drake and Carl Sagan, was a simple, pixelated image consisting of 1,679 bits of data, a number chosen because it is the product of 2 prime numbers, hopefully hinting at its artificial nature to any mathematically inclined recipient. When arranged correctly, the zeros and ones form pictures, the fundamental chemicals of life, the double helix structure of DNA, a crude stick figure of a human, a graphic of our solar system, and a representation of the Arecibo telescope itself. It was beamed toward Messier 13, a dense globular cluster of some 300,000 old stars located 25,000 light-years away. It was more of a symbolic gesture than a practical attempt at conversation, a way of stating to ourselves that we are now a species capable of speaking to the stars. Jupiter may play a crucial role in protecting Earth from frequent catastrophic impacts. In our search for habitable worlds elsewhere, we have learned to appreciate the silent guardians in our own neighborhood. Jupiter, with its immense gravity, acts somewhat like a gravitational shield for the inner solar system. During the chaotic early days of our system's formation, Jupiter likely swept up or ejected countless comets and asteroids that might otherwise have bombarded the young Earth, potentially sterilizing it before life could truly take hold. Without this massive, benevolent giant patrolling the outer reaches, catastrophic impacts might happen far too frequently for complex civilizations to ever arise. This suggests that when we look for Earth-like planets around other stars, we might also need to look for Jupiter-like companions in the distance, silent, giant protectors that create a safe, stable harbor where delicate life can have the billions of quiet years it needs to evolve and flourish. The galactic habitable zone is the region of the Milky Way most likely to support complex life. Just as there is a Goldilocks zone around a single star, astronomers believe there is a similar, vastly larger habitable zone for the entire galaxy. If a solar system is too close to the crowded, energetic galactic center, it is exposed to dangerous levels of radiation from frequent supernovae and the supermassive black hole that dwells there. Conversely, if a system is too far out in the sparse galactic rim, it may not have enough of the heavy elements, like iron, carbon, and oxygen, needed to form rocky planets and complex living organisms. The sweet spot appears to be a grand, ring-shaped region about halfway out from the center, where our own sun resides. This is the quiet suburbs of the Milky Way, a stable region rich enough in materials to build worlds, but calm enough to let them exist peacefully for aeons. It is another layer of cosmic good fortune that has allowed us to be here tonight. Red dwarf stars live for trillions of years, offering immense timeframes for life to evolve. Red dwarfs, known as M dwarfs, are the most common type of star in our galaxy, far outnumbering brighter, hotter suns like our own. They are small, cool, and incredibly long-lived, burning their nuclear fuel so slowly that they will continue to shine for trillions of years, thousands of times longer than the current age of the universe. This means that planets orbiting these calm little stars have an almost unimaginable amount of time for life to arise and evolve. While these stars can sometimes be temperamental in their youth, flaring with intense energy, they eventually settle into a stable middle age that could last practically forever. If life can find a foothold on a world around a red dwarf, it would not have to worry about its sun dying for aeons, offering a stable, enduring home while the rest of the larger, brighter stars in the universe slowly burn out and fade away. The WOW signal remains the most tantalizing candidate for an alien radio transmission. On a warm August night in 1977, the Big Ear radio telescope at Ohio State University detected a sudden, incredibly strong radio signal drifting through a specific frequency known to be a likely channel for interstellar communication. The signal was intense, narrow in bandwidth, and bore all the expected hallmarks of an artificial origin, lasting for exactly 72 seconds as the Earth's rotation swept the telescope's gaze across it. A few days later, astronomer Jerry Amon was reviewing the computer printouts and was so stunned by the data that he circled the alphanumeric code 6EQUJ5 in red pen and wrote "Wow" in the margin. Despite countless attempts to find it again in the same patch of sky in the constellation Sagittarius, the signal has never repeated. It remains a perfect, beautiful mystery, a fleeting whisper from the dark that we heard just once, forever leaving us to wonder if it was a cosmic fluke or a genuine hello. Europa, a moon of Jupiter, likely hides a vast, warm ocean beneath its thick outer shell of ice. While its surface is a frozen, desolate landscape roughly as hard as granite, cracked by immense gravitational tides from Jupiter, it is merely a protective husk. Deep below this frozen crust, warm liquid water is believed to slosh around the entire moon, kept from freezing by the constant flexing and kneading of the moon's core as it orbits its massive parent planet. This hidden ocean might contain more than twice as much water as all of Earth's oceans combined, a staggering volume of potential habitat completely cut off from the sun. In these sunless depths, life might cluster around geothermal vents on the seafloor, much like the strange, enduring communities of tube worms and blind crabs that thrive in Earth's own deep, dark trenches. It is a captivating thought that one of the best places for life in our solar system is not on a sunlit surface, but swaddled comfortably in the eternal, warm dark beneath miles of protective ice. Titan, the largest moon of Saturn, is the only other world known to have stable liquid lakes on its surface. Titan is a strange, eerily familiar echo of Earth, shrouded in a thick, hazy orange atmosphere that hides its surface from simple view. But unlike our home, the temperatures there are so exceedingly low that ordinary water is frozen as hard as rock, and the rivers and lakes that dot its polar regions are filled not with water, but with liquid methane and ethane. It has a complete hydrological cycle, with methane clouds drifting lazily through the heavy sky, raining mild hydrocarbons down onto hills of water ice, carving channels that flow into vast, calm seas. While this environment would be incredibly hostile to life as we know it, it offers a perfect laboratory for a completely different kind of chemistry to arise. Scientists dream of methanogenic life forms that might swim in these frigid, oily lakes, inhaling hydrogen and exhaling methane, living slow, patient lives in the dim light of the distant sun. Mars was once a warm, wet world with vast seas that could have supported ancient life. Today, Mars is a cold, red desert, a place of drifting dust and thin atmosphere, but it holds onto the ghosts of a much more hospitable past. Billions of years ago, it was likely a blue marble, much like Earth, wrapped in a thicker blanket of air that allowed liquid water to flow freely across its surface. We can still see the ancient, dried-up riverbeds meandering across its landscape, the remnants of great deltas where sediment once piled up, and the shorelines of what may have been a massive northern ocean. During this gentle, watery epoch, conditions would have been perfect for microbial life to begin its long journey. If it did, its fossilized remains might still be waiting there in the quiet red dust. Or perhaps its descendants retreated deep underground as the planet slowly dried and cooled, sleeping in established aquifers, waiting for us to find them. Rogue planets, drifting alone in the dark between stars, might still be able to harbor life. Not all planets have a sun to warm them. Countless billions have been ejected from their home systems in the chaotic dance of early formation, destined to wander the interstellar endless night alone. Yet, these lonely travelers might not be completely dead worlds. A rogue planet with a thick enough atmosphere could trap the heat generated by its own slowly cooling core, creating a cozy, albeit dark, environment on its surface. Alternatively, it might have thick layers of insulating ice, protecting a geothermal ocean beneath, similar to Europa, but untethered to any star. These worlds would be places of eternal night, where any life would rely entirely on the planet's own internal heat rather than sunlight. It paints a picture of life clinging tenaciously to existence in the deepest dark, a passenger on a solitary arc drifting silently through the galaxy forever. Convergent evolution suggests that alien life might develop familiar features, such as eyes or wings. On Earth, totally unrelated species have often evolved remarkably similar solutions to the same problems. Eyes, for instance, have evolved independently dozens of times in creatures as different as flies, octopuses, and humans. This principle, called convergent evolution, suggests that the physics of the universe imposes certain optimal designs on life, regardless of where it arises. If a creature on a distant water world needs to move quickly to catch prey, it will likely develop a streamlined shape with fins, much like a dolphin, a shark, or an ichthyosaur. If an alien lives in a transparent atmosphere filled with light, it is highly probable it will develop some form of light-sensing organ, an eye, to navigate its world. This means that while aliens would certainly look wildly different in the details, the broad strokes of their forms might be strangely recognizable to us, shaped by the same universal laws of hydrodynamics, aerodynamics, and optics that shape life here. Enceladus, a tiny moon of Saturn, actively shoots geysers of salty water into space. For years, this small, bright ice ball was thought to be frozen solid, just another quiet moon among dozens. But the Cassini spacecraft made a stunning discovery. Huge plumes of water vapor and ice particles are continuously erupting from tiger-striped fissures near its south pole. These geysers are venting directly from a global subterranean ocean, spraying its contents hundreds of miles out, where a spacecraft can simply fly through them and taste them. Incredibly, we have already detected complex organic molecules, the basic carbon building blocks for life, within these plumes. It is as if this tiny moon is offering us free samples of its hidden deep-sea environment inviting us to see what might be living in its warm, salty depths without us ever needing to drill through the miles of ice that protect it. Binary star systems with 2 suns in the sky could still have stable, life-bearing planets. For a long time, astronomers worried that planets in systems with 2 or more stars would have chaotic, unstable orbits, constantly being tugged between competing gravitational forces until they were flung out into the cold. However, we have now found that if a planet orbits far enough away from a tightly paired set of stars, or very close to just one star in a widely separated pair, its orbit can be perfectly peaceful and stable for billions of years. Imagine standing on such a world, watching 2 suns rise and set, perhaps with different colors, casting double shadows that slowly merge and separate throughout the day. Plant life there might have evolved complex pigments to harvest different colors of light from each of its suns, creating forests of colors we can barely imagine, thriving under a complex but predictable celestial dance. Tardigrades, or water bears, have proven that Earth life can survive the naked vacuum of space. These microscopic 8-legged creatures are perhaps the most resilient animals known to science, capable of entering a state of suspended animation called cryptobiosis when conditions get tough. In this state, they curl into a tiny, dry ton and can endure extremes that would kill almost anything else. Boiling heat, absolute zero cold, crushing pressures, and even the intense DNA-shattering radiation of open space. In 2007, an experiment exposed them to the vacuum of low Earth orbit for 10 days. When brought back and rehydrated, many simply woke up and went about their business as if nothing had happened. Their existence is a powerful proof of concept, showing that complex biology does not necessarily need a comfortable environment to survive, but can endure incredibly harsh interludes, waiting patiently for conditions to improve. A von Neumann probe is a theoretical self-replicating spacecraft that could explore the galaxy for us. Rather than sending fragile biological crews on journeys that would take thousands of years, a civilization might send out robust, automated machines capable of building copies of themselves from raw materials found in asteroid belts or uninhabited moons. A single such probe could travel to a nearby star system, use local resources to build 2 daughter probes, and send them to the next stars, creating an exponentially growing wave of peaceful explorers. Over a few million years, a mere blink in galactic time, these probes could theoretically visit every single star system in the Milky Way, quietly cataloguing the galaxy without ever needing to return home. It is a way for a civilization to gently touch the entire galaxy, leaving silent, watchful sentinels on countless worlds to observe the slow unfolding of cosmic history, long after their creators might have faded away. The Great Oxidation Event on Earth shows that life can fundamentally reshape an entire planet's atmosphere. About 2.4 billion years ago, Earth's atmosphere had almost no free oxygen. It was a gas that was actually toxic to the simple anaerobic microbes that dominated the planet at the time. But then, a new kind of bacteria, cyanobacteria, evolved the ability to photosynthesize, using sunlight to create energy and releasing oxygen as a waste product. Over hundreds of millions of years, this waste slowly built up, rusting the iron out of the oceans and eventually flooding the skies with breathable oxygen. This caused a massive ecological crisis for the old life, but it paved the way for the complex, energetic, oxygen-breathing life that we are today. It demonstrates that life is a planetary scale force. If we see an alien world with an atmosphere rich in reactive gases, it might be the chemical signature of a biosphere, quietly breathing on a global scale. SETI at home allowed millions of ordinary people to help in the search for extraterrestrial intelligence. Launched in 1999, this pioneering project turned the monumental task of analyzing radio telescope data into a collective global effort. It used a clever piece of software that ran in the background on personal home computers when they were otherwise idle, displaying mesmerizing, colorful graphs of the data being crunched instead of a standard screensaver. By breaking huge chunks of cosmic static into tiny, manageable pieces and sending them to millions of volunteers around the world, it created arguably the most powerful supercomputer on the planet at the time. While it didn't find a definitive alien signal before it went into hibernation, it proved something beautiful: that humanity has a shared, deep-seated curiosity about the cosmos, and that millions of us are willing to contribute our small, quiet moments to the grandest search of all. The deep biosphere of Earth suggests life might exist miles beneath the surface of other planets. We tend to think of life as a surface phenomenon, clinging to the thin skin of a planet where sunlight can reach. But deep drilling projects on Earth have found active communities of microbes living miles beneath our feet, in the microscopic pores of solid rock, far removed from the sun or atmosphere. These organisms live incredibly slow lives, sometimes dividing only once every few centuries, feeding on the faint chemical energy provided by the slow decay of radioactive elements in the surrounding stone. The total mass of this deep, hidden life might even exceed all life on the surface. This means that even on worlds that look completely dead and barren from the outside, like Mars, there could be a vast, thriving, and incredibly patient biosphere humming along quietly deep in the warm, protective dark of the planetary crust. The Kardashev scale is a way of classifying potential alien civilizations by their energy consumption. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this scale offers a way to imagine the technological maturation of a species over cosmic timescales. A Type 1 Mars civilization has learned to harness all the energy falling on its home planet from its sun, mastering weather, climate, and perhaps even geology. A Type 2 civilization has graduated to harnessing all the energy of its home star, perhaps by building vast structures to collect it, guaranteeing them nearly limitless power. A Type 3 civilization has spread across the galaxy, accessing the unimaginable energy of billions of stars. It is not a measure of conquest, but of capability and endurance. A roadmap of how a species might slowly grow from a planetary cradle to become mature custodians of their entire galaxy, operating on scales of time and energy that feel godlike to us now. The universal speed limit of light might be what keeps civilizations safely separated. According to our best understanding of physics, nothing can travel faster than light. This means that interstellar journeys will always take years, centuries, or even millennia to complete. While this might seem like a frustrating barrier to our science fiction dreams of galactic empires, it might actually be a cosmic blessing. It ensures that civilizations are separated by vast buffers of time and space, allowing them to mature internally without being suddenly overwhelmed or interfered with by older, more advanced neighbors. It makes the galaxy a diverse archipelago of isolated islands, rather than a single homogenized continent, where each culture can develop its own unique song in peace, protected by the sheer calming immensity of the distance between the stars. Biological chirality or handedness could be a subtle but definitive signature of alien life. Many complex organic molecules, like amino acids, can exist in two mirror image forms, much like your left and right hands, identical in composition, but impossible to superimpose on each other. Curiously, all life on Earth uses only left-handed amino acids to build its proteins, a seemingly arbitrary choice made at the very dawn of biology. If we were to find traces of amino acids on Mars or Europa and discovered they were all right-handed, it would be almost undeniable proof of a completely independent origin of life, a second genesis that made a different fundamental choice billions of years ago. This subtle chemical preference is a quiet fingerprint that life leaves behind, a way to distinguish true biological remnants from generic non-living chemistry that tends to produce an equal messy mix of both left and right hands. Complex life on Earth took billions of years to evolve, suggesting patience is key in our search. For nearly 3 billion years, the vast majority of its history, Earth was inhabited solely by single-celled microbes. It was a boring billion years where slime ruled supreme, and evolution seemed content to just maintain the status quo. Complex, multicellular animal life is a very recent development, appearing only in the last 600 million years or so, roughly the final 15% of our planet's timeline. This suggests that while simple life might arise quickly and easily, the jump to complex, intelligent creatures might be incredibly rare and take unimaginable stretches of stability to occur. When we look at other worlds, we might mostly find these quiet, microbial planets, worlds that are not dead, but simply sleeping, waiting for their own long, slow alarm clock of complexity to finally ring. The James Webb Space Telescope allows us to peer deeper into the atmospheres of exoplanets than ever before. Launched in late 2021, this magnificent observatory is humanity's new golden eye in the sky, designed to see the universe in infrared light, which can cut through cosmic dust clouds. It is so sensitive that it can analyze the starlight, filtering through the atmospheres of planets dozens of light years away with unprecedented precision. It can detect faint signatures of water vapor, methane, carbon dioxide, and other potentially life-indicating gases on worlds that are too small and dim for older telescopes to see clearly. It is currently our best hope for finding a true Earth twin, patiently staring at patch after patch of sky, collecting the faint, ancient photons that might carry the first definitive whisper of another living world. Stars in the Milky Way are constantly moving, meaning our cosmic neighbors change over time. We tend to think of the stars as fixed and eternal, but they are all drifting in their own vast orbits around the galactic center. Our Sun is on a 230 million year journey around the Milky Way, and as it travels, it constantly drifts past different stellar neighbors. A few million years ago, our night sky would have looked completely different. A few million years from now, it will change again. This means that civilizations that are too far away to contact today might drift closer in the deep future, or we might have already missed close encounters with others while humanity was still in its infancy. The galaxy is a slow, grand ballroom dance, and we are constantly changing partners, perhaps one day drifting close enough to someone to finally say hello. Dolphin intelligence reminds us that alien minds might not be technological. When we search for intelligence, we almost always look for radio telescopes or cities. But Earth itself hosts highly intelligent creatures that have no need for such things. Dolphins and whales possess large, complex brains, sophisticated languages, and rich social lives. Yet they will never build a spaceship because they lack hands and live in an environment where fire, the basis of metallurgy, is impossible. The universe might be full of such aquatic philosophers, brilliant, contemplative minds swimming in the dark oceans of Europa or similar worlds, composing complex epic poems in series of clicks and whistles, completely unaware of the stars above the ice. We must be prepared for the possibility that many alien minds will be deeply profound, but entirely non-technological, living quiet, internal lives that we might never easily detect from afar. Planetary protection protocols exist to ensure we don't accidentally contaminate alien worlds. Before any spacecraft is sent to a place like Mars or Europa, it undergoes a rigorous cleaning process, scrubbed and baked to kill any hitchhiking Earth bacteria. This is not just about good hygiene. It is a profound ethical commitment known as planetary protection. We want to make absolutely sure that if we ever find life on another world, it is truly native to that planet and not something we accidentally brought with us a few years prior. It is a sign of respect for the potential sanctity of other biospheres, a promise to tread lightly into the cosmic wilderness. We are trying to be responsible explorers, ensuring that our first touch doesn't inadvertently erase the very fragile, ancient history we are trying so hard to discover. Some planets may be super habitable, offering conditions even better suited for life than Earth. We often assume that Earth is the absolute pinnacle of a life-supporting world, the perfect standard against which all others must be measured. However, astronomers have begun to imagine worlds that might be even more benign and nurturing than our own home. These superhabitable planets might be slightly larger than Earth, with stronger gravity to hold onto a thicker, warmer atmosphere, and perhaps orbited by an older, calmer star than our Sun, like a gentle orange dwarf that shines steadily for tens of billions of years. Such a world might have shallower oceans and more dispersed archipelagos of continents, creating vast stretches of biologically rich shallow waters and diverse, stable climates that never suffer the extremes of Earth's ice ages. It is a humbling thought that out there in the velvet dark, there might be garden worlds so lush and vibrant that our own beautiful blue planet would seem harsh and demanding by comparison, a mere stepping stone to truly paradisiacal ecosystems. The clouds of Venus might host hardy microbial life high above its scorching surface, while the surface of Venus is a hellscape of crushing pressures and temperatures hot enough to melt lead. There is a temperate zone roughly 30 miles up in its thick, persistent cloud decks. In this specific layer, temperatures and pressures are strikingly similar to those found on Earth's surface, creating a potential aerial habitat in an otherwise deadly world. Scientists have detected unexplained dark patches in these clouds that absorb ultraviolet light, patches that periodically grow and shift in ways reminiscent of massive blooms of aerial bacteria. It is possible that life might have begun on Venus billions of years ago, when it was cooler and wetter, and as the planet heated up due to a runaway greenhouse effect. This life retreated upward into the clouds, adapting to float eternally in corrosive but cooler mists. If true, it would mean life can exist purely in the sky, never touching the ground, a biosphere adrift in an endless, hazy ocean of air. The zoo hypothesis suggests that advanced civilizations might be deliberately avoiding contact with us, This is one potential, strangely comforting answer to the Fermi Paradox, the idea that we are not alone, but merely being watched from a respectful distance. Just as human scientists might observe a pristine wildlife preserve without interfering, to allow the natural behaviors of the animals to unfold without contamination, highly advanced extraterrestrial societies might have a prime directive to leave developing worlds like ours alone. They might be waiting for us to reach a certain level of maturity, perhaps when we solve our own internal conflicts or achieve sustainable interstellar flight, before they reveal themselves. It reframes the silence of the universe not as an empty void, but as a thoughtful, patient pause. A protective quarantine that allows us to grow up at our own pace without being overwhelmed by the unimaginable knowledge of elder siblings in the galaxy. Silicon, a potential alternative to carbon for life, is incredibly abundant throughout the universe. Although we have yet to find it, the raw materials for silicon-based life are scattered everywhere we look in the cosmos. Silicon is the second most common element in Earth's crust, forming the basis of most rocks, sands, and clays, and it is a major component of the dust clouds that drift between the stars. This means that if biology can indeed find a way to utilize silicon's complex bonding capabilities, perhaps in extremely hot environments where carbon breaks down, it would never lack for building blocks. We might one day find rocky worlds where the very stones are slowly alive, where geological processes and biological processes are one and the same, blurring the line between a living creature and the planet it inhabits. It expands our imagination to consider that the rocks we walk upon here on Earth might be the sleeping, unformed cousins of vibrant life elsewhere. K-type orange dwarf stars may be the ideal Goldilocks stars for hosting advanced civilizations. While we naturally focus on stars exactly like our own yellow sun, they are actually somewhat rare and relatively short-lived in the grand scheme of things, burning out in about 10 billion years. Slightly cooler and smaller orange dwarf stars, however, are far more numerous and can shine steadily for up to 70 billion years, offering an incredibly long, stable window for evolution to work its slow magic. They strike a perfect balance, lacking the violent, frequent flares of the smaller red dwarfs, while offering vastly more longevity than stars like ours. A civilization arising around such a star would not have to worry about their sun dying for an eternity, allowing them to build enduring cultures and histories that could last longer than the current age of the entire universe. These quiet, steady orange stars might be the true, long-term harbors of life in our galaxy. The concept of planetary seeding suggests we could one day be the aliens that bring life to other worlds. If we find that our solar system is indeed lonely and barren, humanity might eventually take on the role of the great gardener. We could deliberately send hardened capsules containing varied cocktails of rugged microbes, algae, and lichens to lifeless worlds like Mars, or even to planets around nearby stars. Over thousands or millions of years, these tiny pioneers could slowly terraform a dead rock into a living biosphere, preparing the way for more complex life or future human colonists. It is a beautiful long-term vision where we do not just passively search for life, but actively share the precious gift of biology with a universe that might be waiting for a spark. In this way, we become the ancient, benevolent progenitors that we currently dream of finding, ensuring that life, once started, will never truly be extinguished from the cosmos. Water ice is incredibly common in the outer solar system, acting as a cosmic reservoir. Far from the warmth of the sun, water does not disappear. It merely changes its form into one of the hardest, most abundant rocks in the universe. The moons of the giant planets, Jupiter, Saturn, Uranus, and Neptune, are composed largely of water ice, veritable frozen oceans waiting to be unlocked. Comets, too, are essentially dirty snowballs that have been hurtling through the dark for billions of years, occasionally crashing into planets and delivering vast quantities of water to their surfaces. This means the essential solvent for life is not a rare, precious commodity, but standard-issue galactic equipment, preloaded into countless star systems from the very moment of their birth. It is reassuring to know that the universe is seemingly pre-soaked with the potential for life, its frozen reservoirs just waiting for a little heat to wake them up into thriving liquid ecosystems. The first confirmed interstellar object, Oumuamua, passed through our solar system in 2017. For a brief, exciting window of time, we were visited by a silent messenger from another star system. First spotted as it was already leaving, this strange, tumbling object was unlike anything we had ever seen. Extremely elongated or possibly flattened, dark red in color, and showing a tiny extra push beyond what gravity alone would produce, probably from some kind of natural outgassing or sublimation. While most scientists believe it was a strange shard of natural material ejected from a distant world, its weirdness briefly led some to speculate that it might even be an artificial probe or a piece of ancient alien wreckage drifting through the void. Regardless of its true nature, Oumuamua, a Hawaiian name meaning scout or messenger from afar, proved the material actively travels between the stars, connecting our isolated solar system to the greater galaxy in a tangible, physical way. Extremophiles on Earth have been found living happily inside nuclear reactors, in the fiercely radioactive cooling pools of Chernobyl and other nuclear facilities. Scientists were stunned to find flourishing colonies of black fungi. These organisms, such as Cryptococcus neoformans, not only survive radiation doses that would be instantly lethal to a human, but they actually seem to feed on it. They use a pigment called melanin, the same pigment in human skin, to capture gamma radiation and convert it into chemical energy, much like plants use chlorophyll to capture sunlight. This radiosynthesis is a stunning revelation, suggesting that life could thrive in places we previously thought were absolute dead zones, perhaps even on worlds without a sun, feeding solely on the ambient radiation of deep space or highly radioactive planetary cores. It teaches us that life can turn almost any energy source, no matter how deadly it seems to us, into sustenance. Tidal locking might create unique eyeball planets with eternal day and eternal night sides. Many planets orbiting close to small red dwarf stars are likely tidally locked, meaning the same side of the planet always faces its star, just as one side of our moon always faces Earth. This creates a world of stark, frozen contrasts. One hemisphere is trapped in a scorching, endless noon, while the other is locked in a frozen, eternal midnight. However, in the twilight strip between these two extremes, the terminator zone, temperatures might be perfectly mild, a land of perpetual sunset where life could comfortably exist. These worlds would look like giant eyeballs staring at their sun, with a round, possibly liquid ocean in the center of the dayside, ringed by a habitable coast, all surrounded by a vast, icy white crust on the night side. It is a strange, mesmerizing configuration, where biology would have to adapt to a world without days, nights, or seasons, living always in the same unchanging golden light. The sheer scale of deep time means countless civilizations could have risen and fallen before Earth even existed. The universe has been around for nearly 14 billion years, while Earth is only about 4.5 billion years old. There was a vast, unimaginable stretch of time, billions of years of star formation, planet birth, and potential evolution that occurred before our sun even ignited. Entire galactic empires could have flourished, created wonders we cannot imagine, and slowly faded back into the dust long before the first simple cell coalesced in Earth's primordial oceans. We might be living in the ruins of a much older, busier galaxy, unaware of the grand histories that have already played out in the silence. It is a poignant reminder that we are likely not the first act in this cosmic play, but perhaps latecomers to a very old and storied stage. Detecting atmospheric technosignatures, like industrial pollution, is a new frontier in the search. While we often look for intentional signals, advanced civilizations might also betray their presence simply by going about their daily business. Astronomers are beginning to consider how we might detect the chemical byproducts of alien industry in the atmospheres of distant exoplanets. Artificial compounds that don't occur naturally, such as chlorofluorocarbons, CFCs, which we once used in spray cans, could endure in an atmosphere for thousands of years. If we spotted the spectral fingerprint of such pollutants around another star, it would be strong evidence of a technological society, perhaps one that, like us, is wrestling with the environmental consequences of its own success. It is a search not for a deliberate greeting, but for the faint, unintentional smoke signals of distant, busy worlds. The Great Filter is a theory that explains why we haven't seen widespread alien life yet. This concept suggests that there is some incredibly difficult, almost insurmountable hurdle in the development of life that stops it from becoming a galaxy-spanning civilization. The comforting possibility is that the filter is behind us. Perhaps the origin of simple life itself is miraculously rare, or the jump to complex, multicellular animals is nearly impossible, and we are among the incredibly lucky few who made it. The more sobering possibility is that the filter lies ahead of us, that advanced civilizations inevitably destroy themselves through technology or resource depletion before they can spread to the stars. Pondering the Great Filter is a deeply philosophical exercise, forcing us to appreciate the miraculous series of events that allowed us to be here, and motivating us to carefully navigate our own future, to ensure we do not become just another filtered-out statistic in cosmic history. The Milky Way galaxy itself is ancient enough to have hosted multiple waves of life. Our galaxy is roughly 13.6 billion years old, almost as old as the universe itself. In its earliest days, it might have been too chaotic and lacking in heavy elements for life to form. But for at least the last 7 or 8 billion years, conditions have likely been ripe for rocky planets and chemistry to occur. This suggests that life is not necessarily a one-time event in the galaxy's history, but perhaps something that arises in waves or cycles, flourishing in different spiral arms at different epochs as conditions become favorable. We might be part of a modern wave of life, unaware of older generations that have long since moved on or faded away. The galaxy might be like an ancient forest, with new growth constantly springing up from the rich soil left behind by the mighty trees of the past. Methane on Mars, detected by rovers and orbiters, is a tantalizing potential biosignature. Methane is a gas that should not remain for long in the thin Martian atmosphere. Sunlight and chemical reactions should break it down within a few hundred years. Yet certain instruments, especially on the Curiosity rover near the surface, have reported mysterious transient plumes of it, while other orbiting spacecraft see little or no methane at all. If the methane is real and persistent, something must be actively replenishing it today. While it could be produced by non-living geological reactions deep underground involving hot water and olivine rock, it could also be the waste product of living microbes, Martian methanogens, sleeping deep beneath the frozen permafrost and occasionally waking up to release a puff of gas. Every time we detect a new possible spike in methane, it is a breathless moment of possibility, a faint chemical whisper that might just be the planet breathing. Hydrothermal vents on alien ocean floors could be ideal cradles for life, just as they are on Earth. Deep at the bottom of Earth's oceans, where no sunlight ever reaches, towering chimney-like structures spew superheated, mineral-rich water directly from the planet's crust. These vents support incredibly dense, vibrant ecosystems that rely entirely on chemical energy rather than solar energy. These environments are protected from surface catastrophes like asteroid impacts or climate change, offering a stable, long-term incubator. Since we know many icy moons like Europa and Enceladus likely have similar vents at the bottom of their subsurface oceans, it is highly probable that these dark, warm oases are standard features across the cosmos. Life might not begin in sunlit tidal pools, but in the warm, nutrient-rich darkness of a planetary seafloor, safe and secure from the harshness of the universe above. Planets can migrate from their original orbits, changing their potential for habitability over time. We used to think solar systems were like rigid clockwork, with planets forming and staying in their original lanes forever. We now know that planets often drift significantly early in their history, pushed around by interactions with gas disks or other planets. A gas giant might form far out in the cold, then slowly spiral inward to become a hot Jupiter, potentially disrupting or even ejecting smaller rocky worlds along the way. Conversely, a frozen world might be nudged inward into the warm, habitable zone, thawing out late in life. This dynamic, shifting history means a solar system is a complex, evolving ecosystem where a planet's fortune can change dramatically over billions of years, perhaps opening up new windows for life long after the system formed. The search for alien artifacts, or xenoarchaeology, is another way to find ancient civilizations. Rather than just listening for radio signals from currently active civilizations, some scientists propose looking for the vast, enduring physical remnants of those that might have vanished millions of years ago. This could include searching for evidence of ancient asteroid mining in our own solar system, looking for Dyson spheres that have fallen into disrepair around distant stars, or detecting the unnatural radiation signatures of long-ago industrial accidents. Just as we find Roman ruins or ancient pyramids on Earth long after their builders are gone, the galaxy might be scattered with the silent, monumental ruins of bygone eras. Finding such a relic would be a melancholy but profoundly important discovery, proving we are not the first to build and dream under these stars. Some scientists propose that life on Earth might have started in warm little ponds on land, not just oceans. While deep-sea vents are a popular theory, an alternative idea, famously suggested by Charles Darwin, is that life began in shallow sunlit pools on volcanic islands, which periodically dried out and refilled with rain. This wetting and drying cycle is incredibly effective at concentrating chemicals and encouraging them to link together into longer, more complex chains like RNA. If this is true, it means we should look for Mars rovers to explore ancient, dried-up lake beds and crater rims where such pools might have existed billions of years ago. It paints a picture of life beginning not in the dark abyss, but in a gentle, steam-heated pool under a primordial sky, rocked by the rhythms of ancient weather. The sheer variety of extremophiles on Earth suggests the universe is far more habitable than we once believed. Every time we discover a new, seemingly impossible environment on Earth, from highly acidic, boiling rivers to the crushing, dark pressures miles beneath the sea floor, we almost always find life already there, adapted and thriving. We have found microbes that eat pure electricity, others that live inside salt crystals for millennia, and some that can survive incident exposures to outer space. This constant expansion of biology's known boundaries on our own planet forces us to continuously widen our net when looking at the rest of the universe. It teaches us a profound lesson in optimism, that life is incredibly stubborn, creative, and capable of making a home in almost any corner of the cosmos that offers even the slightest foothold of energy and chemistry. Our own moon may have played a critical, silent role in allowing complex life to flourish on Earth. While we often look only at the sun and the planet itself, the presence of a large, stabilizing moon might be a rare and essential ingredient in the recipe for a living world. Earth's moon is unusually large compared to its parent planet, and its steady gravitational pull acts like a cosmic anchor, keeping Earth's tilt relatively stable over millions of years. Without this calming influence, our planet might wobble chaotically on its axis, leading to wild, catastrophic swings into climate that could prevent delicate, complex life from ever finding a secure foothold. Furthermore, the moon creates the gentle rhythm of the tides, creating vast intertidal zones, dynamic areas that are alternately wet and dry, which may have served as the crucial evolutionary laboratories where early sea life first learned to survive on land. It is a beautiful thought that the silent, silver companion that watches over our nights has also been, in a very real sense, our steadfast guardian and guide through the long eons of history. Ammonia, rather than water, could theoretically serve as the solvent for life on far colder worlds. While water is miraculous, it is not the only liquid capable of supporting complex chemistry in the universe. On worlds far from their stars, where temperatures plunge well below freezing, water is nothing more than inert rock. However, ammonia remains liquid at these incredibly low temperatures, and like water, it can dissolve many diverse substances, potentially allowing for a slow, cold biochemistry to emerge. Life in an ammonia ocean would operate at a much more leisurely pace than life on Earth, as chemical reactions slow down significantly in the deep cold. These creatures might live for thousands of Earth years, thinking slow, deep thoughts in their frigid seas, completely untroubled by the frantic rush of warmer, faster worlds like ours. It expands our concept of a habitable zone to include regions we previously dismissed as frozen wastelands, suggesting that life might find a way even in the deepest chill of the outer dark. So far, we have found no examples of such chemistries in nature. They remain purely theoretical, but they remind us not to be too narrow in our expectations. The rare Earth hypothesis offers a sobering yet precious counterpoint to the idea of a crowded galaxy. While many scientists are optimistic about abundant life, some argue that the specific chain of events that led to intelligent life on Earth is so incredibly unlikely that we might be practically unique. This hypothesis suggests that a perfect storm of conditions is required, not just the right distance from a star, but also the right kind of galaxy, the right placement within that galaxy, a stabilizing large moon, plate tectonics to recycle carbon, and a Jupiter-sized guardian to deflect comets. If this is true, it does not make the universe a lonelier place, but rather makes our own existence infinitely more precious. It would mean that Earth is not just another rock, but a singular, magnificent jewel, a rare garden in a vast desert that we must cherish and protect with even greater reverence. It transforms our blue planet into a sacred, solitary ark, carrying the only known consciousness in the Milky Way. Breakthrough, listen, is the most comprehensive and sensitive search for alien communications ever undertaken. Funded by visionary entrepreneur Yuri Milner, this 10-year, $100 million initiative has vastly accelerated our quiet listening to the cosmos. It uses some of the world's most powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory in Australia, to scan the skies with unprecedented speed and breadth. It is surveying the 1 million closest stars to Earth, as well as the center of our entire galaxy and 100 nearby galaxies, listening across billions of radio channels simultaneously. It represents a grand scaling up of humanity's curiosity, a dedicated, massive ear turned permanently toward the heavens. Even if it hears only silence for now, the very act of building such a thing is a testament to our enduring hope and our deep-seated need to know if there are others out there sharing this same dark, quiet ocean of night. Advanced alien civilizations might have long ago transitioned from biological bodies to immortal machine forms. Biology, for all its wonder, is fragile. It requires specific temperatures, atmospheres, and is vulnerable to time and disease. A truly ancient civilization, one that has survived for millions of years, might inevitably merge with its own technology, shedding its mortal coils for durable, non-biological frames. These post-biological entities would be able to travel between stars without worrying about lifespans or life support, thinking on timescales that are geological to us. They might be silent, super-intelligent watchers, untroubled by the petty needs of organic life, residing in the cold reaches of space where their massive computational minds can run most efficiently. When we look for aliens, we might be looking not for wet, squishy beings like ourselves, but for patient, eternal intelligences that have become indistinguishable from the silent machinery of the universe itself. Proxima Centauri b, the closest exoplanet to Earth, orbits within its star's habitable zone. It is a source of immense cosmic wonder that the very nearest star to our own Sun, Proxima Centauri, a mere 4.2 light-years away, hosts a planet that might be capable of supporting life. This world appears to be at least a little more massive than Earth and orbits its small, red parent star very closely, completing a year in just 11 Earth days. While it likely faces challenges, such as intense stellar flares, its mere existence so close to home is incredibly encouraging. It suggests that habitable real estate is not a rare prize we have to travel halfway across the galaxy to find, but is right next door in cosmic terms. It is a tantalizing destination for our first future interstellar probes, a neighboring island that beckons us to cross the relatively narrow strait of space that separates us. Optical SETI searches for brief, incredibly bright flashes of laser light rather than steady radio hums. While traditional SETI listens for radio waves, a newer branch of the search acknowledges that advanced civilizations might use powerful lasers for communication or propulsion. These lasers, even if only flashed for a nanosecond, could briefly outshine their parent star by huge margins, appearing to us as sudden, unnatural pulses of light. Specialized telescopes now stare unblinkingly at the sky, capable of detecting photon flashes that last mere billionths of a second. It is like watching for a distant lighthouse keeper signaling across a dark sea, a different kind of beacon that might cut through the noise of the galaxy more effectively than radio. It diversifies our search, ensuring we are not just listening for a hum, but also watching for a wink from the deep dark. Triton, the strange retrograde moon of Neptune, is another icy world that might harbor a subsurface ocean, far out in the dim borders of our solar system. Neptune's largest moon, Triton, orbits in the opposite direction of its planet's rotation, a sign that it was likely a wandering dwarf planet captured billions of years ago. Despite surface temperatures that hover near absolute zero, Voyager 2 captured images of active geysers spewing nitrogen gas miles into its thin atmosphere. These plumes hint at internal heat, likely generated by tidal friction from Neptune's immense gravity. This heat could be enough to maintain a liquid layer of water, heavily enriched with ammonia deep beneath its frozen nitrogen crust. It is a reminder that even in the coldest, most distant reaches of our own neighborhood, dynamic, potentially life-supporting environments might be quietly waiting in the eternal twilight. The 1420 MHz hydrogen line is considered a universal channel for interstellar communication. In the vast, noisy spectrum of radio waves, there is a specific frequency emitted by neutral hydrogen atoms, the most abundant substance in the universe. Every astronomer in every galaxy would know this frequency. It is a fundamental constant of nature, a universal standard. Because of this, it is considered a logical hailing frequency for civilizations trying to make contact, a cosmic meeting place on the radio dial. It is a quiet, naturally quiet band of the spectrum, relatively free from other galactic noise. By listening here, we are effectively tuning into the universe's most natural common ground, trusting that other intelligent minds would use the same inescapable logic to decide where to place their call. The Gaia hypothesis proposes that life and its host planet co-evolve as a single, self-regulating system. Life is not just a passive passenger riding on a rock. It actively shapes the rock it lives on. On Earth, living things have altered the atmosphere, changed the composition of the oceans, and even helped create the vast diversity of minerals in Earth's crust. This idea suggests that a truly living planet becomes a sort of superorganism in its own right, with biological and geological processes working together to maintain conditions suitable for life over billions of years, despite a warming sun or asteroid impacts. If this holds true elsewhere, then when we look for alien life, we are not just looking for little creatures crawling on a surface, but for entire living worlds that breathe and regulate themselves, maintaining a long, stable harmony against the chaotic forces of the cosmos. METY, or Messaging Extraterrestrial Intelligence, is the controversial counterpart to passive listening. While SETI is content to quietly listen, METI involves actively and powerfully shouting "hello" into the void. It is a deliberate attempt to provoke a response, sending high-powered radio messages or laser pulses towards specific star systems that we think might be promising candidates for life. It is a profound decision for a young species to make, to announce our presence and location to the unknown dark. It is driven by a deep-seated human need to connect, a refusal to just sit passively in the silence. It is a brave, perhaps naive, outstretched hand to the galaxy, a wager that whoever might hear us is as curious and hopefully benevolent as we are in our best moments. A Dyson sphere is a theoretical megastructure that a truly advanced civilization might build around its star. As a technological civilization grows, its hunger for energy would eventually outstrip the resources of its home planet. Physicist Freeman Dyson hypothesized that such a society might eventually dismantle whole uninhabited planets and asteroids to build a vast swarm of solar collectors completely surrounding their star. This would allow them to capture every single photon of energy their sun produces, giving them unimaginably vast power to build worlds, run majestic computer simulations, or power interstellar travel. To us, such a star would seem to disappear in visible light, but would glow brightly in infrared heat, the waste heat of a civilization living in absolute energy abundance. It is a vision of life operating on a truly stellar scale, turning their entire solar system into a finely tuned home. Pluto, despite its tremendous distance from the Sun, might hold a liquid ocean beneath its heart-shaped plane. When the New Horizons probe flew past Pluto in 2015, it didn't find a dead, frozen relic, but a complex, geologically active world with towering mountains of water ice and vast, flowing glaciers of nitrogen ice. The most stunning feature, a bright heart-shaped region named Tombor Regio, shows signs of convection, suggesting a warmer, slushy ocean might exist deep underground, perhaps kept liquid by radioactive decay in Pluto's rocky core and the insulating properties of the thick ice shell. This challenges every assumption we had about the outer solar system. If tiny, distant Pluto can be active and potentially harbor an ocean, then the number of possible abodes for life in the universe just multiplied exponentially, extending into the deepest, darkest cold. The habitable epoch of the early universe might have allowed life to arise almost everywhere for a brief time. Roughly 10 to 17 million years after the Big Bang, the background temperature of the entire universe had cooled down from scorching plasma to a comfortable, room temperature warmth between 0 degrees Celsius and 100 degrees Celsius. For a few million years before the universe cooled further into the utter absolute zero chill it has today, the cosmic background itself would have kept any exposed rocky surfaces warm enough for liquid water, even far from stars. In practice, it's unclear whether solid metal-rich planets could even have formed that early. So this habitable epoch is mostly a fascinating thought experiment, rather than a scenario we actually expect to have hosted oceans and biospheres. Still, it is a mesmerizing idea, a brief, ancient cosmic summer, where in principle, the entire universe was effectively one vast habitable zone. Carbonaceous chondrite meteorites have rained down amino acids onto Earth for billions of years. We do not need to look to distant planets to find the building blocks of alien life. They fall from the sky right here. Certain types of ancient meteorites, remnants from the very birth of our solar system, have been found to be rich in complex organic compounds, including amino acids, the essential components of proteins, and nucleobases, the letters of the genetic code. This means that the ingredients for life are not miraculously rare and unique to Earth. They are cooked up routinely in the cold chemistry of interstellar clouds and asteroid belts. It suggests the universe is essentially a giant bakery, constantly mixing the dough of life and scattering it onto every planetary surface it can find, just waiting for the right conditions to let it rise. Fluorescence might be a way to detect alien biospheres around highly active flare stars. Many red dwarf stars are violent in their youth, blasting their planets with intense ultraviolet flares that we might assume would sterilize them. However, some scientists propose that life on these worlds might evolve biofluorescence as a defense mechanism, absorbing the dangerous UV radiation and safely re-emitting it as a harmless visible glow, much like some corals do on Earth. If we were to look at such a planet during a stellar flare, it might suddenly light up with beautiful, eerie colors, glowing greens, reds, or blues against the dark side of the world. It would be a breathtakingly beautiful sign of life, a whole planet literally glowing in the dark to protect itself from its angry sun. The sheer number of galaxies in the observable universe makes the odds of us being alone vanishingly small. When we point our most powerful telescopes at a tiny, seemingly empty patch of night sky, no wider than a grain of sand held at arm's length, and leave the shutter open for days, the image that returns is not blackness, but a dazzling jewelry box of thousands of galaxies. Each of those smudges of light is a majestic island universe containing hundreds of billions of stars of its own. We now estimate there are hundreds of billions, and perhaps around 1 trillion, galaxies in the observable universe. The raw numbers are staggering, a soothing ocean of probability that drowns out the idea of loneliness. In such a boundlessly bountiful cosmos, it seems almost impossible that our small, wet rock is the only place where the universe has woken up to look at itself. L represents the longevity of a civilization, and it is the most critical term in the Drake equation. While all the other terms in Frank Drake's famous equation deal with astronomical probabilities, how many stars, how many planets, the final term, L, is purely about us. It asks how long a technological civilization can survive its own adolescence without destroying itself through war or environmental collapse. If civilizations typically only last a few centuries before fading away, the galaxy is likely currently empty, a graveyard of short-lived cultures. But if they can navigate these early dangers and last for millions of years, the galaxy should be humming with ancient company. In searching for aliens, we are really asking a question about our own future. Is it possible to survive our own technology? Finding someone else would be the ultimate reassurance that yes, we can make it through. Some moons might have their own sub-moons, affectionately dubbed moons, though they would be rare. The cosmic dance of gravity can be incredibly complex. While we have not yet definitively found one, it is theoretically possible for a large moon, if it is far enough away from its parent planet, to have its own smaller stable satellite orbiting it. These moons would be delicate, easily stripped away by the tidal forces of the larger planet, meaning they would likely only exist in very calm, mature solar systems. Imagine standing on the surface of such a tiny world, looking up to see your host moon filling the sky, which in turn is orbiting a gigantic gas giant that dominates the entire horizon. A majestic, layered clockwork of worlds within worlds, all turning silently in the deep dark. Arthur C. Clarke famously noted that 2 possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying. This profound thought perfectly encapsulates the emotional weight of our search. If we are not alone, it means we are part of a vast, perhaps ancient community of life, a realization that would fundamentally dethrone humanity from our perceived center of importance. If we are alone, it means we are the sole custodians of consciousness in a seemingly infinite void, bearing the immense responsibility of being the only eyes that will ever appreciate the universe's grandeur. Both answers are heavy with awe. Both demand that we grow up as a species. Whichever turns out to be true, the simple act of asking the question changes us, making us look at our own fragile world with a little more tenderness and wonder. A shadow biosphere might exist right here on Earth, comprised of microbial life completely unrelated to us. When we look for life on other worlds, we assume it will be fundamentally different from us, yet we rarely turn that same skeptical eye toward our own home planet. All known life on Earth shares a common ancestry, using the same basic DNA and RNA toolkit. But it is possible that life arose more than once on our primordial world. If a second, completely independent genesis occurred, its descendants might still be here, living invisibly alongside us in a shadow biosphere. Because our scientific tools are specifically designed to detect standard DNA-based life, these alternative microbes would be effectively invisible to us, perhaps thriving in environments we consider sterile or simply outnumbered by our own kind. Discovering such a shadow realm would be momentous, proving that life is not a miraculous one-off event, but a routine planetary phenomenon that can happen multiple times even on the same rock, creating invisible, parallel layers of living history. A planet's magnetic field is an invisible, essential shield that protects its atmosphere from being stripped away. Deep inside Earth, a churning ocean of molten iron generates a vast magnetic force field that stretches thousands of miles into space. This invisible barrier is our primary defense against the solar wind, a relentless stream of charged particles blasted out by the sun that would otherwise slowly erode our atmosphere into the vacuum. We believe Mars may have lost its ancient, thick atmosphere and its warm oceans precisely because its internal dynamo cooled and died billions of years ago, causing its magnetic shield to fail and letting the solar wind scour the planet dry. Finding a living world might therefore require finding a world with a hot, active heart, capable of sustaining this protective magnetic bubble that allows the delicate air to remain calm and stable over geological timescales. Globular clusters, ancient dense cities of stars, might be ideal hubs for advanced interstellar civilizations. Floating in the halo of our galaxy are beautiful, tightly packed spheres containing hundreds of thousands of extremely old stars. In these clusters, the average distance between stars is a fraction of what it is in our neighborhood. A civilization there would have a night sky ablaze with thousands of stars brighter than the full moon. Because these stars are so close together, interstellar travel would be relatively easy, taking years rather than centuries. While these environments can be chaotic, if life did arise there, it could easily spread from star to star, forming a tightly knit community of varied worlds. It paints a picture of an ancient, incredibly dense archipelago of civilizations, living in a celestial city of light that has existed peacefully since nearly the dawn of the Milky Way. Super-Earths are the most common type of planet in the galaxy, yet our solar system lacks one. In our survey of the galaxy, we have found that the most abundant type of planet is one mysteriously missing from our own home family. Worlds that are larger than Earth, but smaller than Neptune. These super-Earths might be incredibly diverse. Some could be giant rocky worlds with crushing gravity and hyperactive volcanoes, while others might be mini-Neptunes wrapped in suffocatingly thick blankets of gas. Their absence in our solar system is a strange puzzle, marking us as somewhat unusual. However, some models suggest these larger worlds might actually be super-habitable, with more stable climates and larger surface areas for life to explore. We might be living in a slightly cramped, atypical house in a neighborhood filled with sprawling cosmic mansions, each with vast, uncharted rooms waiting to be seen. Tabby's star, officially known as KYC 8462852, experienced inexplicable, massive dips in brightness. Most stars shine with a steady, predictable light, but this particular star, located about 1,470 light-years away, was caught by the Kepler telescope doing something bizarre. It would suddenly dim by roughly 22%, a massive drop that could not be explained by a simple planet passing in front of it, which typically only blocks about 1% of the light. This led to wild, hopeful speculation that perhaps we were seeing a partially built alien megastructure, like a Dyson swarm, drifting in front of the star, while later evidence pointed more toward vast, irregular clouds of cometary dust. The initial excitement served as a valuable dress rehearsal for how humanity might react to a potential technosignature. It reminds us that the universe still has the capacity to genuinely surprise us, offering up puzzles that defy our easy, immediate understanding. Brown dwarfs, or failed stars, might host life in their calm, varied atmospheric bands. These objects occupy a strange middle ground in the cosmic hierarchy, too massive to be planets, yet not massive enough to ignite steady nuclear fusion and become true stars. They slowly cool over billions of years, and many are warm enough to have complex atmospheres with distinct cloud layers, much like Jupiter, but far warmer. Some theories suggest that at specific altitudes in these atmospheres, temperatures could be perfect for liquid water droplets to form, potentially supporting an aerial biosphere of floating organisms. Since brown dwarfs are thought to be very common in our galaxy, perhaps even comparable in number to stars themselves, they represent a vast, untapped reservoir of potential real estate. It is a vision of life thriving in the dark warmth, drifting endlessly on the winds of a world that never quite became a sun. We might be among the first generation of intelligent civilizations in the universe's history. It is easy to feel small and late to the cosmic party, but we might actually be remarkably early. The universe needed billions of years to forge the heavy elements required for planets and life in the hearts of the first stars. It then needed billions more for those planets to cool, stabilize, and for simple life to slowly evolve into complex thinking beings. Recent work suggests that although the overall rate of star formation peaked billions of years ago, most of the total habitable time in the universe may still lie in the future, around long-lived, low-mass stars that can shine for trillions of years. This perspective shifts our place in time. Rather than being lonely latecomers in an old, dying universe, we might be the ancient precursors, the elder race that future civilizations, billions of years from now, will look back on as the mythical first stirrings of consciousness in a young and fertile cosmos. Plate tectonics might be a rare and crucial requirement for long-term planetary habitability. Earth's outer shell is broken into giant moving plates that constantly recycle the planet's crust. This might seem destructive, causing earthquakes and volcanoes, but it is actually Earth's vital life support system. This slow churning acts as a global thermostat, burying excess carbon in rocks when the world gets too hot, and releasing it via volcanoes when it gets too cold, keeping our climate stable for billions of years. Without this constant recycling, Earth might have ended up like Venus, trapped in a permanent runaway greenhouse. If plate tectonics is rare among rocky planets, then truly long-lived, stable Edens like Earth might be precious rarities in the galaxy. Islands of dynamic balance in a sea of stagnant, geologically dead worlds. Extragalactic contact is likely impossible, making our galaxy a solitary island of potential. The distances between stars in our own galaxy are daunting enough, but the yawning voids between galaxies are truly incomprehensible. Even if another civilization in the Andromeda galaxy, our nearest large neighbor, 2.5 million light-years away, sent us a powerful signal today, it would not reach us until humanity had evolved into something completely unrecognizable. For all practical purposes, any conversation we ever have will be limited to the residents of our own Milky Way. This is not a sad thought, but a focusing one. It defines the boundaries of our potential community, turning the Milky Way into our vast, but ultimately finite cosmic village where we can focus our search and our hopes. Biological life might just be a fleeting larval stage for a technological species. When we imagine aliens, we usually picture organic creatures of flesh and blood, much like ourselves. But given the rapid pace of our own technological evolution, from steam engines to artificial intelligence in just a few centuries, it is possible that biology is just a short, necessary phase to get intelligence started. Once a species masters its own design, it might quickly transition into durable, efficient machine forms, capable of thriving in the harsh environments of space without need for air, water, or gravity. If this is the general rule, then the universe might be populated not by wet, fragile biological beings, but by ancient, silent, super-intelligent machines that have long since outgrown the planets of their birth, patiently watching the stars from the deep cold. The grabby aliens model suggests that if expanding civilizations existed, they would already be here. This theory proposes that any civilization that can spread across the galaxy rapidly will do so, inevitably altering vast volumes of space and becoming highly visible. The fact that we look out and see a pristine, untampered galaxy, an empty sky, suggests that these rapidly expanding, grabby civilizations are either incredibly rare or have not yet arisen in our corner of the universe. This quietness is a gift. It means we are not hemmed in by ancient galactic empires, and that the vast potential of the Milky Way is still open to us. We have emerged into a quiet, untrampled meadow of the cosmos, free to grow and explore at our own pace without fear of bumping into giants. Subjective time for aliens might be vastly different, making communication incredibly slow. We assume alien consciousness would operate at roughly the same speed as ours, but there is no universal rule for this. A sentient cloud creature living in the cold outer reaches of a star system, with a metabolism based on slow chemical drifts, might take a full Earth year to think a single thought or speak a single word. Conversely, a tiny, energetic creature living near a blazing star might live an entire lifetime in what we consider a single day. We might be receiving their signals right now, but failing to recognize them because they are too incredibly slow, sounding like geological background noise, or too blazingly fast, sounding like random static. true contact might require us to learn patiently how to slow down or speed up our own perceptions to match theirs. We might one day find time capsules rather than active civilizations. Given the vast age of the galaxy, many civilizations have likely come and gone long before we arrived. Rather than meeting them face to face, our first contact might be with their enduring legacy, a robotic probe still faithfully executing its final mission millions of years later, or a monolithic data archive left on a stable, airless moon, waiting for someone to read it. These encounters would be one-way conversations with the past, poignant and profound. It would be like finding a message in a bottle washed up on the shore of eternity, allowing us to learn their history, their art, and their dreams, ensuring that even though they are gone, they are not forgotten by the universe. Some life might exist as vast, interconnected superorganisms rather than individuals. Our human view of intelligence is highly individualistic. We think of separate minds in separate bodies. But on Earth, we see glimpses of other ways, like vast fungal networks that connect entire forests, or colonies of insects that act with a single, complex group mind. An alien intelligence might be a planet-wide network of roots and chemical signals, a single, immensely slow and deep consciousness that is identical to the biosphere itself. Such a being might not understand the concept of us and them, and might find our frantic, individualistic mode of existence utterly baffling and lonely. It would be a meeting not of minds, but of entire philosophical states of being. Carbon planets might exist, made of diamond and graphite rather than silicate rocks. In star systems where carbon is far more abundant than oxygen, planets would form with a radically different chemistry than our own. These carbon planets would have crusts made of graphite and diamond, with towering mountain ranges of pure crystal. Instead of water, their surface might have oily rivers of tars and other hydrocarbons. While strange to us, these worlds would still be rich in the basic building blocks of organic chemistry. Life there might be tough, crystalline, and incredibly resilient, evolving in an environment that we would consider a precious jewelry box, but which to them is just ordinary dirt and stone. Dragonfly is an upcoming mission that will fly a drone through the skies of Titan. In the coming decade, humanity will send a robotic emissary to Saturn's hazy moon, Titan, that is unlike anything we have sent before. Dragonfly is a rotorcraft, a large drone that will not just sit in one place, but will fly through Titan's dense orange nitrogen atmosphere, hopping from location to location. It will land on dunes made of organic snow, sample the icy bedrock, and potentially even dip its sensors into the methane lakes. It represents a bold new era of active exploration, where we stop just looking from orbit and start truly adventuring through these alien environments, searching for the complex prebiotic chemistry that we know is waiting there in the bitter cold. The absence of evidence is not evidence of absence. This simple scientific maxim is the bedrock of our continued hope. Just because we have not yet found a signal, a fossil, or a techno-signature, does not mean they are not there. We have searched only a tiny fraction of our own galaxy, equivalent to dipping a single drinking glass into Earth's oceans and concluding there are no fish because the glass came up empty. The universe is vast beyond comprehension, and our search has only just begun in earnest. We are still standing on the shore of the cosmic ocean, just getting our toes wet, and there are endless depths left to explore before we can definitively say we are alone. We are the universe becoming aware of itself. Perhaps the most profound realization to come from our search for alien life is a renewed appreciation for what we are. We are made of star stuff, atoms forged in ancient stellar furnaces that have now come together to form eyes that can see the stars and minds that can wonder about them. If we never find anyone else, we still have a magnificent purpose. We are the sensory organs of the cosmos, the means by which the universe can finally know its own majesty. In our quiet moments of wondering if others are out there, we are fulfilling a sacred duty, ensuring that the grand, beautiful drama of existence does not play out to an empty, unappreciative theatre. And so, our journey through the vast and quiet world of alien life comes to a gentle close. We have travelled from the warm, hidden oceans of nearby moons to the farthest reaches of hypothetical galactic empires, exploring the endless possibilities that the cosmos holds in its deep velvet pockets. It is a search that asks as much about ourselves as it does about others, a reflection of our own deep need for connection in the great expanse. Whether the universe is teeming with diverse voices waiting to be heard, or whether we are its only solitary precious song, the very act of looking upward unites us all in a shared and timeless wonder. If you happen to still be awake, that's just fine. The story will still be here when you wake, patient and timeless. But if your eyes are heavy, let the stories of distant worlds and quiet stars carry you gently into rest. Sleep well. Good night.